baseline 1 and baseline 2 scenarios. We have a bit more formalization of how we are specifying the pricing for those scenarios. I probably don't need to go into too much detail. Basically, what I'm trying to get is an optimum margin of, and then M here is the aggregate demand at each access or edge node, and I'm tracking the available at each edge node. So what is my model? So basically, I'm now going to specify a model for being able to price the different ways of providing service. First was point to anywhere. Second point to point, and third is point to point plus forward. So that's my demand profile as a sample demand profile. P depicts the marginal price, Q is the demand, and this is the price of service at each node. I depicts the node where this is the aggregate demand at that node, no matter where that demand needs to go, and that's the available capacity at that edge node. So that's my baseline scenario, which is not responding to where the data needs to go, and just look at what is arriving to be shoved into the network and finding a price for it. Note that these are still time dependent, right? So you're still going to respond to how the network changes in time and its available capacity, and how the demand changes in time. So the price is responsive to time-based changes in network behavior. What's not responsive is where the data needing to go. Right? Okay, so which means that in the baseline 2, I'm going to make that distinction. There's a slight unfortunate use of notation here, may not be terribly slight, but in the previous slide I was referring I as an access node or edge node. I'm now using the same I, but now I'm referring to a link, and that's the important point. Right? So the point here now in the baseline 2, to remind you, was we will now have a contract link, multiple contract links in a domain. Each link connects a node to another node, and then each link within a domain is getting marked with 1, 2, 3, 4, and so on. Right? Demanded capacity, the mu I for each link, both changing in time. And then there is the scheme modification of the nonlinear marginal, for which I have to find the optimum nonlinear marginal. So I'm solving an optimization problem on the side, a static optimization problem, find the optimum marginal price structure. And using that, then finding the price of these contracts. So the S here is price of a spot contract for the link I for my domain. And of course, I need to do that for all the links, whichever links I've decided as a provider to produce these contracts on. Okay? So once I have, of course, once I have the definition of the demand profile, which I described in the first slide, and I didn't bother to describe it in detail, I'm continuing to use the same demand profile here, but of course, in this case, that being the optimum marginal price structure, from which I find the spot price. And of course, now I need to find the change in price because of change in demand and available capacity. I would have to use a little bit of math, in this case, the Ito's formula. Okay, so having said all of that in terms of somehow having some structure of available capacity, demand, aggregate demand, I need to specify how those change in time. So these are my time-dependent models for how the available capacity here is changing with time, and the demanded capacity at for each link is changing in time. So these are basically process models for dynamic changes in capacity and demanded capacity. The important point to note here is that, of course, these W's are Wiener processes. The Wiener processes that are driving the available capacity for each link have a correlation. That kind of makes sense. That should make sense because even while I'm in the happy modeling world, assuming these to be some separate links in the domain, in reality, each link is going to be sharing resources. So if one link suffers or experiences a very high utilization or some failures or whatever, it's going to affect the other link. So they don't behave independently. And that's what this part is trying to capture. That the W2s, the Wiener processes that drive the capacity, available capacity, are correlated. So this rho ij term is that correlation term. How ith link affects jth link in its congestion. That's the basic model. Okay, so now I can move on to give a little bit more detail on the third scenario in which I was going to introduce the so-called forwards to be able to sell bandwidth for future. And of course, forwards are well-known derivative instruments in various commodities. So we have a choice of using them as is. Once we have a well-defined definition of a spot contract, we can blindly use them here in defining a forward contract. But the problem, however, is that in a network context where the resources are limited, or at least the resources are capacitated, you can't always be sure come future you'll be able to meet the obligation of the forward contract. The forward contract is obligatory, right? So if you write out a forward, you have to meet what the obligations are come to maturity, right? Which of course in a network context, you're not sure if you have the capacity to meet the contract. So what we need to do is introduce a bailout, a pop-out term there, which is, you're going to have the contract defined such that should the network experience a certain level of congestion, you're going to not meet your contract. There is no other way. Right? That will be our specific definition of a bailout forward. We call it a bailout forward contract, which gives the benefit of a forward both to the provider and the customer, but lets the provider step back should the network get extremely congested at the time when the forward matures. Right? So you're kind of taking the advancement but taking it very carefully to make sure that it's actually useful in the context that you're hoping to make it useful. And the idea, of course, is that these forwards, of course, become a means, a mechanism for creating long-term services. So you might sell spot services as well as forwards. From a customer perspective, you can concatenate these lengths of services to create a long-term service. That's at least one way. And of course, the other aspect from both provider and customer perspective is being able to have the assurance of having the required bandwidth modulo the bailout possibility, of having the required bandwidth when the need arises at a specific price. So you log into a revenue from a provider's perspective and log into a price or cost from a customer's perspective. And in that sense, it stabilizes the revenue and it helps predict the future demand. That, of course, is a given in any forward contract, network specific or otherwise. So we understand the benefit of it, but of course we have to realize that that extension needs to happen, keeping in mind that the network is a capacitated resource. Okay, so having defined that, we go back again to our derivatives book and see how forwards get priced. And of course the forwards the price of the forward would have to satisfy that sort of a differential equation, along with some sort of an end condition, where this would be a plain forward contract end condition, but in this case we have this indicator function which is telling us is the network congested or not. And we have a very simple definition of network being congested, which is the available capacity is higher than a threshold. Right? So if the available capacity at the time the contract needs to start is higher than certain threshold level, wherever you set it, you've defined your definition of where is the network congested. And so that's a given, and when the network is not congested, the forward is honored and hence the game carries on. So in any case, the price of a forward would then, after rearrangement of terms, would basically end up being that. So that's the basic setup. And now, once we've defined these models, we can go into describing applying them. Right? So our objective has been applying them in a very realistic context. So we're looking at these specific network topologies, they're called the rocket fuel ISP topologies, for which we have data for how where the nodes are, how connected they are, what is the capacity of the links, etc. So we want to use a realistic network topology to be able to implement pricing of these contract lists. So which basically means that we have to use the data we have for some sample rocket fuel ISP topologies to populate our models. Basically, populate our models here means that we need to find the parameters in these terms to be able to then use them for finding the prices. So once we have done that, then we'll be able to have the model in a running condition, and we want to run them and see what happens to the prices and how they behave in the three scenarios to compare what the benefit is. How much time do you have? Okay. What I have in the next few slides is how we populate the models. Like I said, we're looking at realistic network topologies with the rocket fuel databases. And from those, we're looking at how in the network topology, how the nodes are connected, what are the link capacities, etc., etc. How do we define a node to be a backbone node and edge node? Of course, you can understand the edge node is at the edge and the backbone is inside the network, right? So we need to define that to be able to then create edge-to-edge paths or links. So anyway, I'm going to skip to the next few slides. They're basically describing, this one is defining a work net topology. You see Chicago, New York, data, and describing their connectivity in a closed sense. And which we need to use to extract information about how we define a node to be edge, backbone, what is the link capacity, what is the demand flow, etc., etc. So we're doing all of that, and I'm just going to animation. So anyway, these guys were describing how do we populate the model, how do we define the parameters to describe how the demand is changing over time, how the available capacity is changing over time, etc. The last point, of course, was that we wanted the capacity to be changing, affecting each other. So this is kind of describing that and how that key rho ij term is getting defined, which was describing how one link affects the capacity of the other link. Right? So without really describing the details of each of those terms, just putting it out once again as a reminder that all the parts would have to be realistically capturing their real-world interaction and how they support the data movement. Okay, so now coming back to the baseline 1, 2, and then introduction of the data forward, and we want to now implement the prices, or implement first the model and then compute the prices based on all the pricing schemes that I mentioned earlier. And this is basically the result. What I'm plotting here is simply a histogram for all the revenue from all the links, or in this case, really all the nodes. Right? So what I have, I'm not quite telling you yet how many different nodes and links there are, but in the histogram sense describing how the revenue behaves if I implement the baseline 1, which remember was a point to anywhere method of pricing, and in which I really have to take into account all the edge nodes and all the data that's getting dumped from each of the nodes and price it. So that's my revenue histogram for two specific nodes, some node 1 and node 5. Doesn't matter, it's just representative two nodes. So that's the baseline scenario. And thankfully the scale is the same, so you can see what's happening at the point-to-point pricing. And it's not surprising, right? I mean, if you did point to anywhere, not responding, being able to differentiate service, you're not getting the benefit of higher revenue from the services that are willing to pay higher, right? So, of course, you see the benefit and it's a no-brainer. But the problem, however, is that we've done that not at all responding to how much more work is it to do a nonlinear point-to-point. There's a computational inefficiency being introduced by distinguishing every link from the other links and finding a separate price for all of them. I guess a scale would be useful if you had, I don't know, 600 different links, right? So then you're basically having to compute prices every time demand comes by for each of those 600 links. And of course, the benefit of that is this revenue. So is that really worth it? That was our basic starting point, right? We want to introduce complexity in pricing to be able to benefit from price differentiation for service differentiation, but we don't want to do it arbitrarily or arbitrary level of complexity. So that's what I have at the bottom here without quite telling you how that came by. That's my so-called reduced BC2. So what I've done here, again, in an illustration, what I've done here, I've drawn the revenue from various nodes. This is not legible, but I have various links here and I've drawn the revenue from each link. So what you see here, there are high levels of clusters. There is not much distinction in revenue being generated from various links. So I don't really have to treat them completely separate, independent. What I can do is I can cluster groups here as though they were indistinguishable and price them identically. That reduces a lot of work, right? So that's what I've done here. I've clustered, I think I have 6 groups here. I've clustered them up, not treating each link distinct. And that's what I'm calling as the reduced BC2. So of course I now have a fewer number of links, and that's the revenue histogram for the reduced case. Okay, so with that now I can move on. So of course one note we would still make is this reduced version still gives me a significant revenue advantage, but I have introduced the price differentiation going from point to anywhere to point carefully without arbitrarily increasing the work or complexity. But remember, I had the benefit of being able to define forward contracts for specific links, and that's what I'm doing here. That's the baseline case, that's the reduced baseline case, not baseline, BC2 case, but the reduced version in which I have complexity controlled. And then I've done now introduction of the forward contract. So what is happening is at any point of time, for the duration of the time that I'm simulating my model, part of the service is getting sold spot, part of the future spot contracts are being sold forward. Right? So what I'm pointing here specifically is 40% of future spot contracts are getting actually sold forward. Right? So of course that results in a certain modification in the total revenue, and as it turns out it actually reduces the total, at least the mean it reduces the revenue compared to the all spot version. So you see that on average the revenue has reduced, but also the spread of the revenue has significantly reduced. Right? Which basically tells us that on average the revenue is lower, but now the variability in the revenue is lesser because you've locked in a certain price for future ahead of time. So it's very interesting to see how this changes by various levels of demand conversion rate. We're calling it CR. So basically, how much of the future spot is the provider willing to sell forward? Right? Of course, a provider has that freedom to decide how much of bandwidth he wants to sell forward. Right? And what is the advantage of that? So you could sell everything forward, which means that you have perfect certainty of how much revenue you will generate, or you could sell a fraction of future demand forward and then leave certain remaining demand with its variability. So that's what this is showing. This is absolutely nothing forward. Since it's almost time I did. So what we've basically done is now creating a pricing mechanism which was conducive to being able to innovate for new service innovations, which are called financial innovations for risk management, for network services that were responding to end-to-end demand or bandwidth requirements within a single domain. Right? So everything that I've spoken about has been for a single domain, but the idea is that if you have a standardized definition of service for a single domain defined by all the various terms I said, time, duration, performance, and financial pricing components, then the standardized mechanism of a solution for a single domain can be used to create end-to-end services. So that's where our research, forward research is now looking at, is being able to look at problems to force the end-to-end creation of services based on what we have created for a single domain in a spot setting or in a forward setting and other risk management tools. So I'm going to stop with that. Thank you so much, class, for such an informative lecture.
Can initiate an action to implement schools and how to have institute in industry interaction. These are the points that we have been talking about maybe for a decade. But what is happening is, are we really and sincerely implementing these things is the question. What are the real problems that we are facing, and to what extent, as business school administrators, we could really manage them? Well, as of now, in Usman University, we have 123 colleges with 10,000 students. Most of the business schools are pawn shops. I am very sorry for making this maybe damaging statement, but this is the case, reality. Yeah, in a public institution or for government organizations, what is the control that you have to instill some kind of quality and utility for the business schools? It's a very big question. We have to think about, the administrator should be conscious about really taking an effective step to make the business schools real business schools, not business shops. Thank you very much.
I propose the vote of thanks.
I thank President Lally for sparing his valuable time and giving the business letter, and also the roadmap for many corporate schools coming up now. And there are many issues where these schools are neglected. But irrespective of the rankings, he pointed out the need for research, the need for governance in these schools, and many other issues. I am sure you will take the important issues and innovative topic. You know that if a country has to progress at the expected rate, especially India, it should have two important things. One is the physical infrastructure, the other one is technology infrastructure. And a lot of investment is needed in physical infrastructure, and also a lot of technology investment is needed. In this context, the topic, the financial innovations in internet bandwidth services, is very relevant. Dr. Aparna Gupta has, in a lucid style, has presented the topic, and that shows the command of Dr. Gupta on the three areas, that is technology, first of all the internet technology, as well as the command on quantitatives, and also the command on the latest